All right, so this is example 2 for this type of circuit. I did sample 1 earlier. Notice this is a parallel circuit, so it's got 3 branches. I've got a current A1, which will be all the current coming from the power source. Remember, the long line represents the positive side, the short line represents the negative side of the power source. So in that particular case, this would be the total current. Then the current splits. Some of it goes down here, some of it goes down here, some of it goes down here. I've got an ammeter in each branch. Notice it doesn't matter whether the ammeter comes before or after the resistor, since within this particular branch or within this branch or within this branch, the current's going to be the same everywhere because those are series branches, or pardon me, within a given branch there's only one path, so it's a series element. But the circuit itself has 3 branches, and so it's a parallel circuit. I've also got a voltmeter across this and a voltmeter over here, which I'll talk about. Finally, I've put a little asterisk here to represent the position of a 15 amp fuse. And I'll talk about what that means in a few minutes. So first thing, as always, is going to be to determine the total resistance. So for a parallel circuit, 1 over the total resistance is equal to 1 over 5 plus 1 over 20 plus 1 over 4. So I'm going to put that in my calculator. It's really easy to screw up with this. So what you want to do when you do that, you want to make sure you put things in the calculator correctly. So for example, I'll say 5, but I'll do the reciprocal button. That might be x to the negative 1 on your calculator, plus 20 plus 4. Now that gives me a total of 0.5. So you might think that 0.5 would be my total resistance, but actually that's equal to 1 over the total resistance. So really 0.5 is the same as 1/2. So I could cross multiply that, or I could just simply use the reciprocal button again, since instead of getting 1 over the total resistance, I want to get the total resistance. So in this particular case, I'll push that again, and I get 2. So 2.0 ohms. So in this particular case now, the power I'm going to use by getting power is equal to V times I. I've got 36 volts, and the total current I don't know yet, so I'm going to have to go down here. So to get the total current, total voltage over total resistance, so that's 36 volts divided by 2 ohms. It's going to be 18 amps. So now I could go back up and use this. 36 volts multiplied by 18 amps. It's going to give me a lot of power. Six hundred and 648 watts. Okay, so now when I look at this, the rest of it should be not too bad. You can choose how to do things in different orders, so I'm going to actually try to figure out this voltage first. That should be pretty easy because voltage across all parallel branches is the same as the voltage across the power source. So in that case, that's going to be 36 volts. Holy cow, and I forgot to put a V1 here. Dang it. So V1 is going to be 36 volts. V2 is going to be 36 volts. V3, however, if you notice, this isn't across a resistance at all. And in Ohm's law, since we know the rearrangement of it would be V equals I times R, I've got current going through here for sure, but I have no resistance in that piece of wire. If it's an ideal wire, we're going to think about it as having 0 resistance. In reality, most wires have a little resistance. We're not going to worry about that. So anything times 0 would give me 0 volts. So in that particular case, this voltmeter would not have any voltage reading. So now going through the currents, we're going to use a rearrangement of Ohm's law. So that's I is equal to voltage divided by resistance. Well, for this branch here, we're going to have 36 volts divided by 5 ohms. 36 divided by 10 is 3.6, so this would be 7.2 amps. Here for A3, 36 volts divided by 20 ohms, that would be 1.8 amps. And here, 36 volts divided by 4 ohms would give me 9 amps. Notice 7.2 plus 1.8 plus 9 will give me 18 amps. That's the same as my total, so the math checks out. The last thing I want to mention is this particular part of the circuit. One of the problems with parallel circuits, now normally we want things to be wired in parallel, because in a series circuit, if you take one circuit element out, everything goes out, because the circuit has to pass through all circuit elements. Here, these are independent, so the electricity passing through this branch doesn't have to go through this one or this one. In other words, if this were in your bathroom and this were a curling iron, a hairdryer, and an electric razor, you wouldn't have to have them all connected at the same time to use any of them. You could use them independently. And the voltage is the same across all of them independently. So this is how our homes are normally wired, is in parallel, because we don't want using one device to affect another device. However, when you have more and more things hooked up in parallel, you can get more and more current, and you can overload a circuit. So if you have something like a fuse box in your home, or circuit breakers, which is usually a gray metal box, there's different circuits for different outlets in your home, and if they go over the rated value, they're going to blow a fuse or trip a circuit, or trip a breaker, meaning that it's going to pop off. And I can talk about why that is a little later, but the main thing is it's a safety issue. The exact mechanism for how, again, I can talk about later. So if you have more than 15 amps going through this, and this particular circuit's only rated for 15 amps, that means the wires would have too much electricity going through them. They get hot, they could potentially catch on fire, and that could cause your wall to catch on fire where things are, the wiring is located. So we definitely don't want that to happen. So in this case, this would overload. It would blow the fuse because it's rated for 15 amps, yet we have 18 amps going through this part of the circuit. So that's a safety mechanism in homes to make sure you don't have electrical fires.